proof?
Yeah.
So
in SL, in SL, please correct me if I forget something, because I solved it like a week ago, and I don't quite remember what all this means. So we need to prove that in this guy, please remind me the formulation of the problem, because I only have the solution.
You need, for this Lie algebra, you need to show that abstract Jordan decomposition and coincides with the Jordan decomposition for linear operators.
Yeah. So to do this, so what's the Jordan decomposition? It's decomposition into a nilpotent part and into a semisimple part. Right?
Yes. Yes.
So, and in the context of the standard Jordan decomposition, this means the following: like the in each matrix can be decomposed, can be written as a Jordan normal form, where like we have some eigenvalues on the diagonal, and on the diagonal, which is one
upper subdiagonal, I guess. Yes.
Subdiagonal, we have
ones. Yes.
Or
Okay.
ones, or just like zeros, depending on the multiplicities of the eigen values.
Right.
So, and what we prove is like we remember what the SL2C consists of. So which elements form the basis in SL2C? And then
SLNC.
SLNC. I'm sorry. SLNC. And then they prove that these these elements indeed fall into one of, like here the decomposition into the semisimple part and in the nilpotent part is like these guys are nilpotent, and
yes.
these guys,
yes,
these blocks are semisimple. And
right.
we prove that all basis elements of SL and C can be represented either in this way or in this way. And
what do you mean by that? Represented
so
either in
we
this
have
way?
Two types of elements in the basis of SL and C. We have EI, which are, let me use the direct notation. Is this clear? What does this mean?
Yes.
Okay, and we have such elements.
I would prefer if you write HI for the first one.
Okay, yeah, that will be more in the
common,
accordance
yes, okay.
with, notation on our edge. So, and what we want to prove is that, okay, so first, it is evident that the adjoint action of HI on HI is just 0, because they commute.
Yes.
So, now we want to prove that, like, we want to check what is the adjoint action of HI on EJK.
And maybe HI, HJ, right?
Yeah, that's right.
Also, your H looks exactly like U, but okay, I think we can cope with that, since you don't have U.
Okay, so, and here there is a technical calculation, but at the end we got that this is also 0.
HI adjoint to EJK for... I don't think it's true.
It's not 0.
It's not. Cannot be.
No, it's
this is a root.
So
this is a root vector in our.
Sorry, it's
so
not.
It cannot be 0.
I just read everything that's here, and then it's like it was a wrong turn in my
Okay.
solution.
So what's the correct?
Yeah. The correct one is that okay, we have a formula. So at HIEKL is, and then we consider different cases. So we have a set of 3 indices here, and we consider different cases dependent on.
But I think it's just like that. Correct me if I'm wrong. It's just delta I k minus delta I l.
I'm not sure if this is the final.
That's exactly how roots. That's exactly problem number maybe 3, right? You need this computation.
Because like here I have a very long.
Yeah, I understand, but is that?
No, so what I've got as the expression for this guy is like delta I k E I L.
Ah, yes.
minus
Sorry.
delta,
Yes.
I plus 1
Mhm.
k E I plus 1
Mhm.
L.
Yes. I'm kind of no. I'm wrong. Yes. So what you're writing is correct.
K I delta I plus E.
I'm already thinking in H's, so that's one H.
Delta L I plus 1.
Yes. Okay.
This is the expression.
Mhm.
And then we can see, because this expression is so complicated, we consider a special, as like we separate our problem into a list of special cases. When,
But wait. Sorry. This already means.
It's hard to see what exactly it means, because there are so many indices here. So
Right.
we decompose it like into a set of special cases, and
Mhm.
for each case it's evident what it means, and what's the form of of the matrix for it.
Mhm.
I think the important thing is to think that this is a diagonal matrix.
Yes.
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 Just look at it and it will be.
Well, it's not. Yeah. It is. It turns out to be a diagonalizable matrix.
So you would like to diagonalize at UHI, right?
Yeah.
Okay.
So, and we consider, as I said, a set of special cases, because like here we have a lot of deltas, and we consider the case, so we have a lot of constraints.
Maybe we don't need like all the details, but what you're doing here, you're showing that at HI is diagonalizable in basis EKL, right?
Yes.
Okay. So this thing is semi-simple.
Yes.
Okay, so that's one thing that we need. All right. So then what?
Yeah. So then comes the next thing. So now we want to like first add Ej Hk is just minus at Hk Ej, right?
Yes.
So this case is it can be reduced to the previous one, and what's left is to calculate the final part at KL E and N.
Mm-hmm.
This guy. And the expression for this guy is okay, and the expression for this guy turns out to be so it's at EKL delta Lm minus so no wait I'm sorry. So okay, the final expression for this guy, because there are a lot of calculations here as well, is at EKL. Oh, I'm sorry, EKK delta Ln minus EKK delta NL delta Lm minus delta Km. No, I'm sorry again. Here I have also considered a lot of different cases, so it's like a special case as well, where is.
So, Vadim, sorry, you just need to formulate what calculations is okay, but when you try to put them on board, it kind of takes a lot of time. So just need a goal. Why do you need? Okay, global goal. We formulated, right?
Yes.
A Jordan decomposition abstract is the same as Jordan decomposition's linear operators, right? And I think what you're trying to say is that at HIs is semisimple, right? That's what you would like to check. And at EIJ is nilpotent.
Yes.
So all your cases, all your
yeah. Okay. Now I remember what happened. So I just acted 2 times by that geometry.
Okay, so suppose we check that. Okay, maybe.
So first we act like by at EKL by EMN, and and here we have M does not equal to N, and K does not equal to L. Because that's the restriction on EML and on EMN and EKN.
Sorry. So let's agree that we already proved this. So now what's your next step? Before even writing any formulas, can you say in words? So it's very important to
the next
formulate a goal.
Is to use the linearity, because
okay, linearity is okay. We can apply that, but for what? Use linearity to compute what?
Any element of our SLN
yes
is a sum of elements of H, is a sum of these elements
yes
with some coefficients.
yes.
And by linearity, we can decompose this into a sum of coefficients, into sum of elements which are semisimple, and into sum of elements which are nilpotent.
And this is
nilpotent is nilpotent. Sum of semisimple is semisimple.
Right, I agree. Yes.
So any element of SLNC is a sum of a nilpotent and semisimple.
I would little bit worry about sum of nilpotent. It's nilpotent, but still I think is okay if you apply it on one element. This is not so like for sum of semisimple is semisimple. I mean, you just take a matrix,
yes,
right, and write it in the form. So you will just have HIs, right, and consider Jordan normal form of it. You'll have HIs with some coefficients plus BIs with something like AI I plus 1.
Yeah.
So that will be exactly your Jordan decomposition as linear operator.
Yeah, but I think the indices for B like I'm not sure if here the index.
So this are either 0 or 1s. These are your eigenvalues,
Yes.
right? So therefore this is Jordan. But then you just say, okay, this is Jordan decomposition as linear operators. But then add hi is semisimple, right? And this is upper triangle matrix. Of course, if you start, applying, okay. So then this is semisimple as abstract in abstract Lie algebra sense, right?
Yeah.
And you just need to prove that this is nilpotent in abstract.
But like, haven't we proven this already? Because
you have to check it.
okay, we check that it's nilpotent by acting twice by the joint representation of this guy onto like a general element, and the this the second power turns out to be always 0. And this is what I checked. So like it's confused me. It has confused me a bit because I forgot.
But it's a bunch of elements, right? So you have sum over I here.
Yeah, they are all.
So, but the thing that it's this is xn, right?
Yes.
And the xn is nilpotent. So you don't even need the fact that it's something like this, right? We just need to check that xn is nilpotent is in abstract sense, right? Then we are done. But what does it mean? It means that you would like to check that add xn to some power k is 0.
This power is 2. So that's what I checked.
I don't think so. I don't think it's...
because we like... okay, at least it is 2 for the
it's
the action on...
It's 2 for such...
for the action on the same type of element.
Okay.
It's...
yeah.
Maybe we can just choose any nilpotent matrix and say that a joint is also nilpotent.
So, like, you see what I can just write it down. Let's first, when acting with E high KL on E M, and we get E KN delta LM minus E M L delta N K, and then they act the second time with the joint representation on this guy, and we obtain. At E K L E K N delta L M minus at E K L E M L delta M K, and this turns out to be E K K.
But you're not saying that it is 0, right? If I apply it the second time.
It is.
Cannot be true.
Like it's not. So.
I think you have some mistake because in general it's not it's not 2. It's not that simple. But you don't need all this explicit things. You just say, okay, what is add xn, right? You take an element y. If you apply add xn to y, what it means? You apply multiplication from the left minus multiplication from the right. Right? So this is L xn, so some operator like this, minus of y, right? Minus multiplication from the right applied to y. These two guys commute, multiplication from the left and multiplication from the right commute, right? And also, since xn is nilpotent, if you multiply from the left sufficient number of times, it is 0. And from the right, it also be 0. So therefore, Lxn and, sorry, here I have to write R. R and xn are nilpotent, and they commute. So I can consider Lxn minus Rxn to some sufficient power, I don't know, 2k. Yes. And then this since they commute, you can just write it down by binomial, by Newton binomial, right? And you will see that in each term, your power, either for L or for R, will be greater than k. And this will be 0.
Yeah, okay, I thought about this, but I just, like, if you take this formula
Yes.
and substitute it yet another time for EKN and EML,
Yes.
like action for the second time with the same parameter.
Mhm.
Like what you got is
But you will not get 0. That's for sure. If you got 0, then some computational mistake.
It's okay, just I substituted and I got this.
Okay.
And like this guy, it does not look like 0, but it is essentially 0 because it's because of all these deltas.
Mm-hmm.
So like
I understand what you're saying, but in general, this k that you choose is not 2.
I think okay, it's not true because
Otherwise,
I think it's not true.
Our life would be too simple.
When acting on it's not true acting on the on something that contains besides these guys also guys from some other, like also guys from HI, I think.
No, you can take large enough matrix with once on subdiagonal, and still you still have to apply add a bunch of times. Okay, so but at least this one is that clear. Okay, thank you. All right, so
no, I think it's like it is not. It is nilpotent of degree 2 specifically when you act in the adjoint representation on another element of like on another projector from like if you have.
I understand, but you have yes, but then you need to consider sum, and what you do with sum, that's I don't know.
And okay, and with sum you apply like this.
But they do not commute. You cannot apply Newton binomial if your terms do not commute.
Like the other guy is an eigenvector. So the other type of guys are all eigenvectors.
So of different eigenvalue. No, that's
like the thing is, on each step you can substitute real numbers or complex numbers instead of these. It doesn't matter instead of these guys.
No,
so if you
sorry. So okay, let's discuss after that if you.
Actually, we need to consider. Okay. We need to prove this. And okay, let's write. So this for any x from algebra. Commutator is 0. Any h from h. And normalizer. have to consider two sides. First is,
Mhm.
I think it's evident that C lays inside normalizer because
Yeah, it's
because
obvious.
zero is
Obvious, yes. Mm-hmm.
how I wrote, yeah, how it looks in page. Oh, stop. Okay.
Okay.
Yeah, and second is we want to prove that N lays inside C, and for that we use that it's, I don't know, definition, proposition, something that if I don't know, like this, if H is Cartan subalgebra.
Mm-hmm.
Subalgebra in J, obviously. So any element we can write like decomposition. So we consider element x from n, and that element we wrote like x like h plus h with index number 1 plus h with index number 2 and etc. So this h is it's from h, and this is not from all this h. So they all not from this. Yeah, and what we need to do is that to consider commutator. Actually, that's all.
Can you be more specific? What is this decomposition that you're writing? For example, I can just take so I don't know. So what?
Like in definition, it was written that we can do that.
Yes.
Yeah,
Okay. So this is a root decomposition. Okay. Mm-hmm.
Okay, I will put it here also for any case.
Mm-hmm.
Alpha from R and all that J alpha, that's not coincide.
Mm-hmm. So your lambda 1, lambda 2, they are roots, and H lambda 1 lives in G lambda 1, and so on, right?
Yeah.
Okay. Mm-hmm.
And then we need to consider the commutator x k. That's k lay in H, and if you will put instead of x this, it will be.
Mm-hmm. So your x is a normalizer.
Yeah, and this k, and now because it's 1 second, yeah, because it's linear, I can say that I can open
Sure.
brackets, so it will be hk plus the 1 k plus and I don't know, maybe it's important to say that they are infinite, finite. So it will be plus h lambda n.
Sure.
It's also will be h lambda n.
Mm-hmm.
Etc. H lambda n. Okay. And this will be 0.
Yes, because H is commutative.
Yeah, and
Mhm.
1 second. This also will be 0.
It should be lambda
So how K lives sorry.
In H.
K lives in H and H lambda 1 lives in G lambda 1. So H lambda 1 is an eigenvector of K with which eigenvalue?
Yeah, so that's also will be 0 and everything is 0.
Wait, not so fast. Yes. So what is this guy?
H lambda 1.
So I claim that this guy is some multiple of H lambda 1 as well.
Okay, and
So H lambda 1 is an eigenvector of at K.
okay.
Why? Because it lives in G lambda 1. And G lambda 1 is eigenspace of all H's. I mean, all elements from H, right? So in particular, this one. So if I apply a commutator to this one, I will get this element multiplied by some number, right?
Okay, yeah.
So this number is so it's H lambda 1. And what is this number? What's the eigenvalue of action of K on this? Remember, eigenvalue actually stays in here. So this is lambda 1 of H of K, sorry, times this, right? But this number is even not important. It's just to recall what's going on. Yes, minus. Thank you. Yes. So what's important is that it is inside G lambda 1 again, right? Because this guy is in G lambda 1. It's just multiple of this guy. So this commutator, the next one is G lambda is inside G lambda 2, and this one is in G lambda n. So this, since X is a normalizer, it means that if I apply, it's still in, so the whole thing is still in H. So what's written on the left is in H. What's written on the right is in this cement, right? So the only way, and they do not intersect. So the only way to this to happen is for this guy to be 0, of course. Yeah. So 0 is indeed true, but you need to be more specific why. Yes.
Okay. Right. So I can trick.
Yes. Yes. Yes.
Okay, I'm also.
No, very good. So you're almost there. Okay. Any comments? Questions?
I
Objections?
solved it in a different way without use of the group decomposition.
You just can choose a basis, right? And in a similar way.
I at least not at least I didn't choose a basis explicitly. I just considered all elements that don't commute on 0 with H,
Mm-hmm.
and then I claim that the span of these elements is a solvable proper ideal, which contradicts like the fact that this algebra has no non-trivial proper solvable ideals.
No, interesting. Okay. Yes.
So like there is a subalgebra of which is the union of the span of all elements which don't commute on 0 with H, and of the Cartan subalgebra. One can easily prove that this is a subalgebra, and in this subalgebra,
But you need to prove that it's ideal, and you would like to prove that it is solvable. Right?
Yes. No, that I prove that this algebra has a solvable ideal, which is which is the Cartan subalgebra itself.
But if you have subalgebra that has a solvable ideal, then it doesn't mean that this ideal is of the whole algebra.
If G is semisimple, any of its subalgebras is also semisimple. I construct a subalgebra, and I prove
No,
this.
no, I don't think that's true what you're saying.
That's one of your
No,
statements on,
every ideal is semisimple.
uh,
For example, take, I don't know, SLN. Okay.
like I think in one of your lectures.
No,
there
every
was a literal statement. That's,
yeah, it's about
semisimple subalgebra can be like any subalgebra of a semisimple algebra is it's sum of you just choose some of these direct of elements of this direct product of this direct sum.
Mhm.
And like any choice.
No, that's not true. You at least you can take a one-dimensional subalgebra, which will be abelian. It's not semi-simple. That's the easiest counterexample to what you're saying. What I proved is that any ideal of semi-simple algebras is semi-simple.
But
Okay.
this guy is also ideal, I think.
Okay, then you have to prove that it's ideal. Okay, anyways, so let's continue. And then 5.3 was about roots of right, of SLN, right? Maybe Sanchita. Okay.
Okay, for the part that it is the corresponding roots, I didn't explicitly solve them. I just wrote that idea. This is how we can do. I didn't do the last computations.
Okay.
But I'll give the rest. Okay, so the question is that prove that the diagonal matrices of SLNC form Cartan subalgebra, and then we have to find the corresponding roots. So first, for the Cartan subalgebra, we have this definition already,
Mm-hmm.
and so let's say H1, comma H2 is in. This is, let's say, okay. Some metrics in the elements of SLNC, we can write them as, EFH. Is that okay?
This is for SL2.
Yeah, okay. I don't remember the notation, but we have several E's and F's and H.
We had, but you need to specify what you mean.
Okay, well, I will try to.
You can, okay, so you can start with SL2 if you wish. And
Okay.
then, if this helps, I don't know.
I can say that, okay, the matrices are of the form of n plus, n minus, and H is the diagonal matrices. These are the lower triangular matrices, and these are the upper triangular matrices.
This is perfectly okay. Yes,
so
okay.
they are corresponding to EFH. Okay, so I can do, okay, I want to prove that the set of, this is from SLNC, so I can say the set of matrices which commute with the diagonal matrices will form for H to be Cartan subalgebra, I have to find the decentralizer and then make a statement that is actually equal to H.
Yes.
So I can take these matrices and then try to see how the commutation relations hold. And we know that the diagonal matrices commute with each other.
Yes.
Okay, but with the n plus and n minus, no. The upper and lower triangle, we have a specific relations when we do that.
With some, they commute. I mean,
Yeah,
yes. I mean, the idea is there, but you need to choose specific. So okay. So idea is what you take. So what you need to do? You need to take something from centralizer, right? So what it means? It means that you take a matrix that commuting with any diagonal that commutes with any diagonal.
Yeah.
Okay. You would like to see that it is diagonal as well, then. Right?
Yes.
So then you're done. Then you proved that what you have is a Cartan subalgebra.
Yes. So okay, the way I understood was that out of these three kind of matrices, The diagonal matrices will commute with these two. No.
So, yeah. So you would like to right. So you're saying that you would like to check that for upper, for lower triangle, and for diagonal. For diagonal, they commute.
Yes.
So it's I don't think it's a correct statement that n plus. So what does it mean n plus doesn't commute?
The upper triangular matrices do not commute with the diagonal ones.
I mean, I can give you upper triangular matrix and diagonal that will be commute. It depends on matrices.
Okay.
Right.
So
For example, I can take cell 3, right? And let me take this one, and this is a cell 3, right? And I don't know, this one. Of course, they will commute.
But we don't have these kind of matrices in H, right?
Yes, we don't. So I can, okay, let me take SL4.
Okay.
Doesn't really matter. You have to be still specific, right? What? So actually, remember that we actually checked. Maybe we checked what is the center of like GLN.
Yes.
This were diagonal matrices, and this check is kind of the same. So what you would like to see is that, okay, you take some diagonal matrix, right? Well, it's from SLN, therefore the sum over diagonal is 0, right? But still, it's some diagonal matrix, right? And well, no, you take some x, right? Such that x with t is 0, where d is like that for every d1, dn, such that the sum is 0.
Yes.
So the idea is to take d to be, di's to be pairwise distinct.
Yes.
Then, so if you commute, what you have? If you multiply from the left, you multiply what? I don't know, rows or columns by d's. I think if you multiply from the left, you multiply rows. If you multiply from the right, it's columns, or the other way around. But anyways, if you have off-diagonal entry in here, right? When you multiply from the right, it will be multiplication from one di.
Yes.
And if you multiply from the left, it's another di.
Okay.
Like dj. Since they are distinct, right, and the result is 0, you have like a factor of di minus dj there.
Is it?
So this entry should be 0, xij.
Okay. Is it corresponding to the root decomposition that we get lambda and minus lambda kind of thing?
Yeah, well, it's kind of related, but still it's like it's a concrete thing, right? So you maybe we can even write this down explicitly, right? So you so if you are computing xd, right, commutator, and ijth entry.
Okay.
Right. Even maybe so yeah, to maybe to recall. So let's see. So we have d1 dn multiplied by x11 x1 n xn1 xnn, right? So from the left, I will have, I think d1 x11, d1 x12, and so on. And here I have d2 x 1, 2, 2, 1 here. So, right, d2 and so on. Here d3 x. So here I multiply columns by these,
Yes.
right? If I take the other way around, right, here I have x's by these, right? I will have, I will multiply rows. So I have d1 x11, and here d1 x12, and d1 x13, and so on. And then d2. So now d1s and d2s, they change like that.
And then the
So it's then this minus this should be 0. So look at here. So I'll have d2 minus d1 times x12
yes.
should be 0. And if I choose d2 minus d1 different, it means that x12 is 0.
Yes.
And in the same way, like all xij's are 0 if I is not equal to j.
Okay.
So therefore, it means that my x should be diagonal.
Okay. Okay, it's a more generic statement.
Yeah.
But okay, can we do it something like this as well? That we have a central algebra class with g lambda and by sum over r.
Mhm.
And okay, then we will have, okay, if we consider just the case of SL2C, we will get a plus 2 and minus 2 when we do the commute element from here, some x belonging to this whole thing, and then try to do the compute this.
Okay.
Okay, but what will that give me? Actually, I will need to think more about this.
Yeah, so maybe the same thing, but here it's pretty explicit.
Yes, yes.
I'm still not sure. Is it rows or columns here? Okay, you tell me. How I multiply row by column, right? Like that.
This is row probably, and this is column.
Yeah, I think I'm wrong. I think I have d1. D1 goes by row here, then 2, 2, 2. And here, like that, d1, d2, d3. But doesn't really matter, still d1 minus d2 times
Yes.
of the diagonal.
Okay, so as
Okay, so Cartan, we proved that it's Cartan.
yes, and then the other part was to find the roots.
Yeah.
Okay, I didn't do the whole computation.
Maybe somebody else would like to show what are the roots.
Okay. Okay.
So roots are elements of H star, right? So these are
Yeah,
linear
I want
functionals.
To describe like H star,
Uh-huh.
it's actually some operator. It's this operator over a relation.
Mhm.
Where each operator is because it's over diagonal matrices, right?
Sure,
So
yes.
each operator, like for example AI, when acts on the one, on the I,
Mm-hmm.
on the N,
Mm-hmm. Just use
we
lambda
just
I.
give lambda I.
Okay.
All these matrices, they are of trace zero, right?
Right.
So
So
that's
therefore
why
you
we
have
take,
this relation.
Yeah.
I agree.
Relation.
Mhm.
And so. What else I have to do? Like, okay, this is all, and we want to.
We want to find which ones correspond to roots, actually, right?
And actually, maybe I should put this, but at the end we will have is this combination.
Mm-hmm. Yes. Okay. This is very good. It's very helpful to understand what's the goal, where to go, right?
Yeah. So
Mhm.
this is we can check that it's each matrix Ej. It's eigenvector of this operator. Well,
Of
not-
which
not the
operator?
eigenvector. Yeah, it's no. Sorry.
It should be eigenvector of all diagonal matrices in SLN, right?
Yeah.
Yeah. So that's what you're doing is very good. So
Yeah.
you have you need to show that there is a vector, right, which is common eigenvector for all right. So fix some I and j, right, and maybe right. So you would like to see that there exists some vector v, depending on I and j, so maybe ij, right, such that h, if I take some h from diagonal matrices in SLN, acting on Vij, right? Well, action is what? Adjoint action, right? So gives me Ei minus Ej of h, right, times Vij.
Yeah.
So now you're claiming that your Vij
It's
is Eij, right?
Okay.
And now you just need to check this, right?
Okay. So I have to take this H as diagonal matrices, right?
Yeah.
So let's take Ij with some diagonal matrix like H, as we say.
Mm-hmm. Yeah, you can follow what you wrote there. It's not.
I
Yes.
just put in general and I have to retake what I wanted to say in this. Okay.
No, the idea is for you to do that, to do it your way. So I'm just.
It's because
Yeah.
just when we take this
Okay.
for this side,
Mhm.
we will get it's like to act with.
So H is diagonal and traceless, right?
Yeah, but I think this
The-
would be like to get. I think this is the same as this. No.
So your H is also Ei, maybe, right?
No, because I have to act on the diagonal matrices. Let's check because.
No,
It's like all the elements of G is like this and like that.
yes. So you take, maybe you can take, so my suggestion is take H first. It will not be in SLN, but whatever. Just
So
for,
the diagonal.
yes, just Ei.
Ah, okay. Yeah, okay.
Then maybe not EKK, right? To not to intersect, to confuse indices with this one.
Okay.
Yes. Then what?
So. have
Mm-hmm. Mm-hmm. Right.
We want this to be eigenvector, right? So
Yes, yes. Right, so we want this to be an eigenvector for the action of H.
like lambda ij. In this way? No.
Mm-hmm.
So
But did we compute this right?
I think yes, because we want because this will be 1, so this has to be j.
Mm-hmm.
This will be 1, so this has to be I.
Mm-hmm.
So it has to be eigenvector in some way.
Mm-hmm.
Always, so just to see that it's yeah, okay. Yeah, so it's in both cases can be represented as this one. Yeah.
Yes. So your H is actually EI.
Because, okay, yeah, to see that the eigenvalue appears here, it's
Yes.
consider a kk with a lambda there.
Mm-hmm.
So yeah, it should appear a lambda here and here. But,
Yeah, but still we would like to have just EIJ, right?
it's because I remember. Yeah, like if we index the lambdas here, like lambda something, it
Mhm.
would appear lambda j here.
Mm-hmm.
And lambda I here. So at the end it would be like lambda j and lambda I. So I can say that it's E sub j and E sub I again on this.
Mm-hmm.
So I have to change this. Okay, then,
Okay, just do what you did in your
Okay.
computations, then
Yeah.
then we'll see.
okay, maybe a bigger one, like
Mm-hmm. Yes. Okay.
maybe more explicit.
Yes. Yes. Very good.
So it's j. We will call it with lambda.
Mm-hmm. Okay. Mm-hmm.
There will be lambda j. Minus
Minus lambda I EIJ. Yes.
and this is the same as lambda j minus lambda I and j.
Okay. Yes. Very good.
Same as ej minus
Of lambda, right?
yeah, of lambda. Lambda this.
And that's it, right? Exactly. And this from here to here, just explicit computation, right? Okay, thank you very much. Yeah. Always, there was, I think, here you still can go explicitly, right, to find like a basis and all that stuff, but it's kind of getting messy, right? So, but I don't know.
That's what I did. Okay.
It can be done like in different ways still, but I mean,
Yeah, I would like to know what are they looking
okay, so let's see.
I will show what I did and then
Yeah.
you tell me
Uh-huh.
other.
If it's messy or not.
Yeah. Okay, so we need to prove this first. This is our D, our
Yes,
algebra,
yes.
and we want to prove that the matrices generated by these elements in this form, they are. This is Cartan subalgebra.
Mm-hmm.
Oh.
Mm-hmm.
We need to prove this is Cartan. Actually, I think my solution is ugly solution because I was working with generators and I took a basis.
Mm-hmm.
So I define this H1 to be this matrix.
Okay. Mm-hmm.
My H2 would be
The similar, but this block goes to the bottom. Yes.
Yeah.
Okay. Mm-hmm.
So I will just you see it's like H1, but you do this switch.
Yes.
Okay, that's
Clear. Okay.
E1 would be this.
Mm-hmm.
We have this algebra. It's 6-dimensional, so we will have our 6 generators.
Mm-hmm.
I will write them here.
So now you are just writing what eigenbasis,
Yeah.
common eigenbasis for H, right? Thus proving that it is toral.
Just
Okay, whatever.
1 second.
Yeah,
I will explain
Mm-hmm.
my idea. This is E1, E2, and then it remains to write F1 and F2. These are all generators in my algebra.
Mm-hmm.
So it remains to have this one. Oh, and okay, and F2. And we have okay. So this is our basis.
Mm-hmm.
And what I did in my solution was to perform the commutation relations
Okay.
here. So we will have the following relation. So when we compute H1, E1, we will get minus F2.
So this basis is not eigenbasis yet, right?
No.
Okay. Mm-hmm.
No.
It's just some natural basis for SO. For C. Yes. Okay.
I will write just the relations and
Mm-hmm.
and I will explain then what I did. So I have this. I compute this in mathematics.
Mm-hmm.
So I got these relations. Okay, so now the proof. We want to prove that the H, which is generated by the first two,
Mm-hmm.
this is Cartan subalgebra. So I consider, okay, again we need to prove that CH equals H.
Okay.
This is the goal. So if you take any element in SO4,
Mm-hmm.
X, this X is a linear combination with these elements here.
Right.
So when I compute X is arbitrary. X with HI,
Mm-hmm.
it can be 1 or 2.
Mm-hmm.
When you have the contribution from H, this is going to be 0 immediately in this bracket.
Right.
So then you are
it remains to compute the parts that are with this, like something
I
like
agree.
this.
Yes.
Yeah,
Okay.
right? You will get something like x 1, 2, 3, x 3. This is 1, 2. I want to write this here. I. Sorry. I mean.
So alpha are coefficients, right?
Something like. The component. I will decompose the.
Yeah. So maybe x equals to. Yes. Okay.
Wait, you see?
No. Yes.
Fi, H. But we know that this, by the commutation relations that I computed before, this E with I, we can see this here. It goes to the span of the F matrices. The H with the E. And the same with this. You're not getting. You're staying here, generated by these guys.
Right.
So if you want this to be in H, you by this. The only way this is in the span of the H is that these contributions are 0. So you get that the constants, these alpha i's that appears in the expansion, in E i's and F i's, they must be 0.
Okay.
So at the end of the story, you get that that x is in H, in this thing. So
But you actually would like this not to be in H, you'd like this to be 0. But still, what you're saying is true. Yeah, since you're taking centralizer. Yes.
Okay, so now I would like to find the decomposition. And I want to talk about the roots. So,
But technically, you didn't prove that it's Cartan, right? Yet.
Why not?
You need to prove that each element is semisimple. Of course, it's abelian, right? But each element is semisimple means it's diagonalizable. That's what you're going to do now, right? You're going to give me.
What I was doing next was to write the matrix for at H1, at H2, and I made the diagonalization of this.
It means that you diagonalized at H1 and H2. It means that H1 and H2 are semisimple. So yes.
Right. So I compute this thing, the matrix in this basis for at. And
Okay.
it's easy. We just need to look at here, and of course it's important the order that I have put. This is like my first component, second, third, fourth, and so on. So we just plug the coefficients here, and we get the following matrix. I will just write the thing. The rest of the thing is just 0. This is the thing.
Okay.
Then this one. For this, you will have.
Sorry, your basis is which one? H1, H2. Then in the order you wrote E1, E2, F1, F2, right?
This is 1, 2, 3, 4, 5, and 6.
Okay.
Yeah. So then I plug the coefficients here, and I got this matrix for at H1, for at H2, I did the same. So the first two columns are zeros.
Okay.
Yeah.
Yes.
Okay. So we know this will be the G0. And we see we do this next. And here are the eigenvectors.
Okay.
Okay. So now here I will have. That's okay. I don't know. This is so. It's not. Maybe it's not the efficient way to.
No, you do it in straightforward way by very clean, so it's understand. No, well. It's
Okay. So then what I did once I got this thing.
Is it really like that, or maybe? So this are in the same row, right? These negative ones.
Oh no no. Sorry. Yeah. No no. I mean.
Maybe
It's
here.
It's here. Sorry.
And
It's
then,
here.
so 1, 2, 3, 4,
Three.
5, 6, yes.
Okay, like this.
Mm-hmm.
And then I took this matrix and I compute the diagonalization between the eigenvalues, eigenvectors.
Mm-hmm.
And okay, I want just to sum up the result. The eigenvalues that I found was plus, minus, I, and 0.
Mm-hmm.
And the same for this one. Plus, minus, I, and 0 are the eigenvalues.
All right.
So, okay. So I want to find now you see the
Basis in which
Yeah.
it's diagonal. Okay. Mm-hmm.
So I wanted to find the roots.
Mm-hmm.
I mean, we know these alphas or this lambda, whatever,
Mm-hmm.
they are in H star.
Right.
But here we can think of this linear functional as a tuple, as a row vector.
Mm-hmm.
It means, I mean the following, if I have AB, this is in H star, this is the linear functional for which A apply in H1, for which this is A and for which this is B.
Okay.
Okay?
Yes.
So I maybe I will make a picture better, because here, how can I say it? Sorry, here is one. Here is one. Was correct? Okay, so associated to these eigenvalues, I will have vectors. I found these vectors.
Mm-hmm.
And then I wanted to have common vectors for these matrices.
Right.
So I take, for example, when I took the following possibility, let's say I minus I.
Mm-hmm.
So then I just write the linear combination of the vectors in the eigenvectors of H1 with eigenvalue I.
So is this the same notation that you explained there, right?
Yeah, yeah.
Okay.
But this is my first root. I'm not taking the 0 because this is the space generated by H.
Yeah, roots
So,
are not
so-
0, okay.
And so we want to do this. I want to find this part,
Mm-hmm.
the ones that are not
Mm-hmm.
trivial
Right.
subspaces. So this is what I want to find here. So I just took this, I minus I. So for this, I need to find a common vector of
Mhm.
H1 and H2, and with eigenvalue I associated to this operator, and with eigenvalue -1 when I
Mhm.
apply this operator.
Mm-hmm. Mm-hmm.
So then I found this because for this one, in principle, the eigenspace generated by I here
Mm-hmm.
is a two-dimensional one.
Okay.
I found two vectors here, and for minus I here, I found two vectors.
Mm-hmm.
So then I wrote a linear combination here of these two vectors with I, and here the same.
Such
then-
that it is
Yeah.
antisymmetric, right?
And then I equate the two vectors,
Mm-hmm.
and I solve you see, for the constants, for
Mm-hmm.
the coefficient, and then I found the vector.
Mm-hmm.
And in this case, my vector is given by this. I call this V1.
Mm-hmm.
So I found this vector. I don't know if it's clear, I hope.
Mm-hmm.
I found this. And then you see, we have minus alpha, V minus I. And I did the same procedure, and I found the vector for this.
Mm-hmm.
This is lambda 1, in my notation this is lambda 4, and this is what I call lambda 4, and I found this vector, and it is this guy, I 2 plus F1. Yeah,
And you have other two, right?
yeah, the one that is linear independent with this row would be II. So I will have II minus I minus I. This I call them lambda 2 is this root. I think, oh, no, no, what I'm doing. I mean, II, just II. And my lambda 3 is minus this. And with the same procedure, I found the common vectors there. So in total, we have these 4. They are linearly independent. And the other, the remaining 2 are associated to this with 0 eigenvalue.
Okay.
So that's, I don't know, that's what I was doing.
No, okay, that's straightforward, but again, very clean. But I have one question. Why didn't you take, try to find I, 0 root, something like this? Right, so you have this 4, right? And you're choosing these values, right, from the values here, right? But in principle, you might have a root like something like I0, right? Because you have also zeros.
I think what I think is it can be done, and maybe it's not unique the root system that you take. I think you can choose many of them. Not really. Okay.
No. It is unique. It is just like that.
Okay.
These eigenvalues, after all, right? So this is spectral data. Of course, if there's no such thing, because you kind of exhausted everything, right? You have 4, and the other 2, you have also 0, 0 of multiplicity 2, right? So you kind of you kind of gave me everything, right? So there is no such things. But why you started with this? Maybe just.
No, I just was trying things.
Okay.
And it worked, so that was all. And now, okay, I have a question.
Sure.
With the previous problem, because Abner was writing something. I think you wrote EI minus EJ, something like this. But I was writing things like this by something that we studied in the previous semester. You got these 2.
Right.
Minus 1, 2 here, minus 1, then 0. So when I solved the problem, I took my first functional was just with 2 here, minus 1, and like this, and I got these things, and I don't see how this is related to this notation that he was using here.
So this is SLN weight, right? And we have GLN weights and SLN weights, right? If you remember previous semester, and SLN weight is exactly so how to get. So this was SLN, right? How to get GLN out of SLN?
Oh, but why GLN? The problem was about SLN.
Right. But this is in terms of this is in terms of GLN. You just this quotient that is taken after that,
Okay. He was
right?
taking the quotient?
Yes.
Oh,
So he takes exactly the diagonal, but this is in terms of H. Is either you take EII or HI, which is difference of 2.
Oh, yeah.
So that's the difference between what Abner wrote, and he just like enforced this relation by quotienting.
Oh yeah, I remember.
Yeah,
That was the first one.
yeah.
I was forgetting that. Yeah, okay. I think that's true.